Hi there.
Hello.
How's it going?
Going well. How are you?
Good.
What's on your wall behind you? I see that there's like a stack of 4 pictures.
The two at the top are service awards. The one facing is a service award. The one below is an award, and the small one is my college degree.
Nice. Wait, what kind of services were it?
One is for 20 years of service, 25 and 30.
Wow.
Look, the gas is out in my building. Can you come right over and fix it? You know something?
Michael, David will be very happy to do it for the right price.
Name your price.
I don't think you can afford it, Michael, but for the right price, David will be very happy to do it.
I'll give you any service award you like.
We only take cash.
You know something? The last time we had a gas problem on this block, it took Con Ed 3 months to fix it.
Come with the whole crew.
And they had to give, fortunately it was across the street from me. It was not on my side of the street. And they had to give everybody in the buildings that were affected, they had to give them hot plates.
Yeah.
I told them they should hire a lawyer and sue Con Ed, because I mean, what they had done was entirely unacceptable.
Probably one of the pipe risers failed. The pipes that go up to feed the buildings, they probably failed a pressure test.
Well, they had to replace all the pipes. They were drilling in the street for weeks and weeks.
Yeah, they may have lost the building while they were working on something, and when they went to turn it on, they couldn't turn it on because there may have been a leak in one of the building risers.
Yeah. What kind of work did you do? Were you in a managerial type position?
I started out in a union in working for electric operations in the survey department. Then I worked as a design technician in gas engineering. Then I went into management, and I rotated around the construction, distribution services, engineering, and I landed back in engineering in major projects, gas operations. And my last assignment was in construction management.
And were you at Irving Place? Or?
I was in Irving Place, I was in the Bronx, I was in Queens, but I had jobs all over.
But you didn't know my high school friend, Artie Osterweil. I know I ask you this every time we discuss this.
When did he retire?
I don't know. I lost touch with him because he was friendly with me and my girlfriend at the time, and she retained the relationship with him and his wife. But I know he's got a son who's a professor at Berkeley. He's a psychology professor. Wow. I mean, I never knew his son. It was too many years ago.
Was he in gas operations or electric operations?
Well, he was an electrical engineer. So we both went to City College and studied electrical engineering together.
Okay.
But I don't really know what he did at Con Ed. Kind of lost touch with him when he took that job.
Matt, how was your move? How was your move?
Oh, my move. Oh, it worked out. Yeah, it worked out okay.
You're still in New Jersey?
Yeah, I'm in New Jersey now. You know, my brother and I lived in this apartment in Philadelphia, and he moved to Rochester. So we gave up the apartment, and now I'm back here, living at home, South Jersey.
All right. South Jersey, that's a bit far away, but I was going to suggest that once you're done with the virus, we can have meetings right here in North Jersey. In Jersey City.
Yeah.
We have a very nice place. we can meet here.
Yeah, someday we will meet again in person.
Yeah.
Are you in touch with Spencer, Matthew?
Not as much as I'd like to be.
Why doesn't he tune in? He actually gave a presentation at the New York meetup.
Yeah.
I don't think you
A
were there.
series of presentations.
Yeah, but on Kruskal coordinates, I remember.
Yeah.
But I mean, he could tune in unless he doesn't wake up until the afternoon. He's
Yeah, I
in
got to talk to
California.
him. I was also wondering where Victor went. He hasn't been around in a little bit.
Yeah.
Gotta.
Well, I don't think Victor is as technical as the rest of us. So maybe he.
I liked it. It's true, but he's a smart cookie, you know.
Oh yeah, he's a smart guy. Yeah.
Gotta talk to him. Well, guess let's get started. So I'm gonna send a little link to the chat. The notes for this are not in the usual place. I put this together actually kind of for like a different purpose. I was like applying to this this thing, and they ask you to do like a little quantum problem, and so I wrote up this little tutorial about the variational quantum eigensolver. So I thought I'd talk about it here. So to get the goods, go to this link. It's on my GitHub. It's worth mentioning that, like, I guess partially because of that, this is going to be easy if you guys want to like run the code yourself locally. You can even do basically like we're going to like run it on a quantum computer, and you can even do that like right from the binder. If you you can do this actually with the code that I normally put up. I don't know if I have talked about it in a while, but if you guys know about Binder, it's worth mentioning. It's a great tool. I don't know if you guys are all familiar with it. Basically, if you put stuff, like Jupyter notebooks, like on a GitHub, you can associate this like a binder to it. It's like a free service. They get this funding from all sorts of people, and it allows you to run your Jupyter notebooks in the cloud. So I recommend if you want to follow along there, and you can also run this thing locally. You'll see, and in fact. Like, okay, well, here's the question. Have any of you used one of IBM's quantum computers before?
I used PC Junior.
Wait, say that again?
I used the PC Junior. I used to work for IBM, and when the PCs came out, they gave everybody a PC Junior. I mean, it was a real piece of junk.
That's pretty cool. I recommend it. There's like several, really existing, quantum services out there today. I think in the past I talked a little bit about like Rigetti's, which is great. One of the differences with IBM is that, you sort of like submit your circuit or whatever, and then they put it in a queue, and then it kind of like runs, after like a couple minutes or something. Whereas for Rigetti's, at least when I used it before, you would sign up for like a time slot, and then you'd sort of get, free use of the thing at that time. So, if you sign up for the IBM service, it's free. You'll be able to get into this pane here where you look at, like, for example, here's like all the quantum computers that they have freely available, not too shabby, 5 qubits, 15 qubits, and you can see, which ones have like a lot of jobs queued up. They even have like a sort of a fancy classical simulator here. So for example, because sometimes it can take a while, let's just run this code that we're going to talk about right now, so that later down the line, it'll be ready for us. So, you know, again, I'll explain all this stuff in a second. So this guy's running. And
Hey, Matt.
yeah.
I don't think you're sharing yet.
The screen, so real, so true. All right, there we go. Okay, you guys see that? Yes, my apologies for that. Okay, yeah, here's the GitHub page. I sent the link. Here's the Jupyter notebook as a binder. You know, if you click on launch binder down here, you can access that. Here's this like little internal thing for the IBM system. As I said, you can see these quantum computers that are available for use here on the side. And I ran this little code here. Well, you know, I'll explain what this does as we go on. But I just wanted to have this queued up. You can see here now that these 4 jobs are now pending. And in, you know, approximately 20 minutes, they'll be ready for us to look at. So we'll have that chugging away in the background. Yeah, I recommend playing around with that. Oh, Moshe dropped out. Moshe's coming back. Let's give him a second. Oh, here. Okay. So we got these jobs queued up. We'll see what they do. We'll check back in on them in a little bit. Okay. So let's get started here. Variational quantum eigensolver. Pretty simple. We're not gonna like do anything super fancy with it. We're just gonna sort of talk about the principles involved. You can, it's sort of like a very general class of algorithm. And, you know, there's all sorts of fancier things you can do. But when you get started, you know, there's a couple basic things that, you know, you need to understand. And that's what we sort of are going to talk about today. So, you know, the basic problem to be solved is, for example, maybe you want to find the lowest eigenvalue / eigenvector of a very large matrix. Maybe that matrix represents the energy operator of some quantum system whose ground state you're interested in. Maybe not. Maybe you have some other motive. Maybe, who knows? You know, maybe it's a completely classical problem that you're trying to solve. Nevertheless, you want to find some eigenvector. And if this matrix is super large, you know, it's going to be a pain to solve for its eigenvalues and eigenvectors using, you know, the usual techniques. Now, today we're going to focus on like literally like a 4x4 matrix just for simplicity, but, you know, the principle is the thing. So, you know, you could try solving for the eigenvalues and eigenvectors, but you might wonder, hey, if we actually had a quantum system, we could evaluate expectation values. Like if H here represents our energy operator, you know, concretely represented by some matrix, if we had a quantum computer, maybe we could, you know, calculate this expectation value. Could we use that to help us? What if we had some kind of ansatz, great word, ansatz, you know, which means a kind of a structure, a kind of hypothesis about what your answer is going to look like, some kind of structure that's parameterized and that you're going to sort of fill in. Like, for example, you know, if you're not familiar with that word, like a neural network is like an ansatz in a sense, right? It's like some kind of structure, a bunch of, neurons connected to each other, and you know, you're basically trying to train the parameters of that thing. So for example, if you had an ansatz for your eigenvector, call it alpha, maybe it takes some parameters, like for example, one parameter, an angle theta. You could imagine searching over theta until we find a value of theta that minimizes this expectation value. And then you solved your problem if you're looking for the lowest eigenvalue eigenvector. And you could do that search using all sorts of interesting stuff. In this little tutorial, we're just gonna we're gonna use just theta, and we're gonna search over 2 pi, but you could use trickier stuff, stochastic gradient descent, whatever you like. And in fact, at the end, I'll talk a little bit more about that. There's a cool idea I was reading about called quantum natural gradient descent that, there's another quantum computing company, Xanadu, who has some frameworks such as Strawberry Fields and Penny Lane. All their stuff is named after like Beatles songs, which do sort of quantum machine learning, and they provide some useful tools for that. But we'll come to that later. So, okay, so classically, we're given a matrix. We could try solving for its eigenvalues and eigenvectors if we're interested in them, but if the matrix is really large, that's gonna be hard. Maybe we have a quantum computer, we can evaluate an expectation value. We could come up with some ansatz, if we're smart, for our eigenvector that we're looking at, and then we could search over theta until we find the value that minimizes this quantity, this expectation value, and then we've solved our problem, because then alpha evaluated at whatever the right theta is will give us our lowest eigenvector. Okay, so that makes sense, but you might wonder, how do we actually measure something like this expectation value on a quantum computer? Depending, quantum computers come in different forms. I'll talk more about that, this company Xanadu, for example, they give you, they're sort of photonic-based quantum computers. So, you're given basically a bunch of like, harmonic oscillators to play with. Maybe you have, what we're gonna talk about here is like if you have a qubit-based system. And, it's worth going over this because, you sit around playing, with your pen and paper and you're calculating stuff. Well, at the end of the day, when you have your quantum computer, it's like they give you, n qubits, right? You can like, apply some unitary gates or whatever. But at the end, they basically let you measure the qubits along the z-axis in the end. And you get a bit, 0 or 1, and that's it, right? So like the only measurement like built in that you're gonna be allowed to do is just to measure each qubit individually along the z-axis. But we wanna measure this. We wanna do this kind of thing. So how do we essentially implement arbitrary measurements of like arbitrary operators on our quantum computer, given that all we can do is measure the n qubits individually along the z-axis? So that's sort of the essence of what we're going to talk about today. So as an example, suppose we have that H is this little baby matrix here, a little 2 by 2 for negative 2i, 2i, 2. Okay, you look at that. Okay, well here's our Pauli matrices. We know and love them. If you you just sort of look at them long enough, you might realize that like we could write H as actually something like 3 plus 2y plus z. In other words, you see here, you're like, okay, 2 times sigma y, that gives us our 2i and negative 2i. You add this in there, then, that plus that gives you the 4 there. That gives you a 3 minus 1, you get a 2. So we can actually decompose this little operator as a sum of weighted Paulis. And if you think about it, by the laws of expectation values, the expectation value of this operator, and I'd sort of simplify the notation here, this just means like on some state psi, you know, that this and this, by that, I mean the same thing, it's just a little, you know, shortcut. We could write this expectation value as the sum of the expectation values of these Paulis multiplied by this weight in the decomposition. So we could, you know, basically get a bunch of systems, you know, all identically prepared, try to find the expectation value of Z and Y, and then that'll actually give us the expectation value of H. For any 2x2 Hermitian matrix, Hermitian operator, we can do this. In other words, we don't have to eyeball, you know, the Paulis and just try to like guess, you know, what linear combination of them is going to give us our matrix. We can just do it systematically by, you know, taking the inner product, taking our matrix and basically finding its component in the direction of each of the Paulis, because the Pauli matrices, they all are orthogonal as matrices, and they form a basis. So, you know, up to this little factor of a half, you know, you just take the trace of, you know, the Pauli matrix times H, and that gives you a number. And that gives you these numbers, in fact. So, you know, just for, just to see it go down. Here's our Paulis. Here's a little function that takes, you know, the operator and finds its decomposition in the Pauli basis. So we go through each of the Paulis and we take the inner product. We normalize it a little bit here. We can also go in reverse. We can take each of the terms in this decomposition, multiply the weights by the Paulis. That'll recover the original matrix. So we can look at that. So here's our matrix that we like. We call this function, and look, it decomposes it exactly as we predicted. 3, 2, and 1 are the weights for the identity. Pauli Y and Pauli Z. We can sum them up again, and we indeed get the original matrix back. Okay, does that make sense? We can check, in fact, that this statement is true. So, you know, what we do here is we choose a random state. We calculate the expectation value of H the usual way, you know, which is by like wedging the operator in between psi, you know, adjoint of psi and psi. We get this number, 2.06, blah, 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 blah. You know, that depends on what this randomly chosen psi was, but we can also calculate it the Pauli way in the sense that we go through the decomposition and we get the expectation value of psi on each of the Paulis, get that expectation value, so expectation value of Y and Z, for example, multiply them each by the weight in the decomposition. So we multiply, you know, the Y1 by 2 and the Z1 by 1. And in the case where we don't have anything here, where it's just the identity, we don't have to do anything at all. We just, you know, add 3 to the result. It's just a constant factor. And if you do that, you see you get exactly the same number. So just sanity check there. That is in fact how expectation values work. Okay. So we've reduced the problem of measuring H, the expectation value of H, to that of measuring the expectation values of, X, Y, Z's separately, which is progress. Like I'm saying, your quantum computer is going to give you the ability to measure in the Z direction. That's just built in. So, that presents us no problem. If we want to calculate the expectation value, all we do is we prepare and measure some, large number n of identical copies of our initial qubit. We get up or down each time. Over the course of the experiments, we accumulate the counts, the number of up, number down, divide them by the total number of experiments, and we get these probabilities for being up or down. We associate up with eigenvalue 1, down with eigenvalue -1, and then we sum the probabilities weighted by the eigenvalues. And indeed, that's the definition of the expectation value of this. Or, another way of saying it, we do our experiment a bunch of times, write down a 1 or a -1, depending on each outcome, sum them all up, and divide by n, the number of experiments. And, just to make this like concrete, it's like we can calculate the expectation value of Z in the usual way, just use like Q-tip's built-in function, which is, the same thing, just take psi dagger on H on psi. And we can also sort of estimate it stochastically, like, so I just like literally do it here, in kind of a dumb way, right? It's like I take psi, I get the density matrix, right? Which is gonna be a 2x2 matrix, and the probabilities are gonna be along the diagonal. And then I flip a coin, just a pseudo random coin. And I get 1 or -1 with those probabilities, add them all up, divide by the number of experiments. And you see, you get, something that's pretty close to the, exactly calculated result. I just do this, because, once you're working with the quantum computer, you got to sort of like, you're like interpreting like all these like measurement results that this thing gives you. And so, it's worth just sort of simulating it out here classically. Okay, so that's all well and good. But what about, measuring the expectation value of X or Y? This is just going into it very, we already know this, but, we'll just, for completeness sake, we'll just say it again. As we know, where do those probabilities come from? Probability of up and down in the Z direction anyway, right? Like they're the, squares of the amplitudes for our qubit state, little two-dimensional state there. We could also write as this, linear combination of up and down. As we well know, the state can be interpreted as a point on a sphere given by the expectation values of X, Y, and Z, plus a complex phase. And we well know that the two complex orthogonal eigenstates of a Hermitian matrix, like X, Y, and Z, they're orthogonal as complex vectors, but geometrically they correspond to antipodal or opposite points on the sphere. So that, the eigenvectors of Pauli Z are the North Pole and the South Pole, and the eigenvectors of Pauli X, are the two opposite points in the X direction, and similarly for Y direction. And in fact, any 2x2 Hermitian matrix, its eigenvectors will be opposite points in some direction on the sphere. And, just because I like it, I mention here again the fact that you can also get that same result using our favorite thing, the stereographic projection, where we get the, instead of taking these expectation values, X, Y, Z, oh, look at that. Our quantum computation finished. Look at that, beautiful. We'll come back to that, okay. Was it really was that all 20 minutes? It all passed by so quickly. Okay, instead of taking these expectation values, we can just, if we have these amplitudes, we take the ratio of the amplitudes. That gives us a complex number, which lives, say, like here on the complex plane. We project that onto the unit sphere, and we get the point on the sphere that we like. The point is, that, like, looking at the, the state vector, it's just like a two-dimensional complex vector. It lives in a Hilbert space. Kind of abstract seeming, but, like we can associate it with a rotation axis that's built out of expectation values. And so I emphasize this because, like, in a way, that solves our problem of measuring, the expectation value of y and x if all we can measure is the expectation value of z. If we want to measure x or y, all we have to do is rotate our qubit before we do the measurement. So, like, for example, if our qubit was pointed, in the y plus direction, that's going to mean a y measurement is going to give us up every time, but we're only allowed to do z measurements. So we can get the same effect as a y measurement by just first doing a rotation of 90 degrees or pi over 2 around the x-axis, which is going to rotate y plus into z plus and y minus into z minus. So we can turn a z measurement into a y measurement by first applying a 90-degree rotation around the x-axis, which, is an exponential of Pauli x, like that. And remember, when you're doing this, when you're doing the Pauli stuff, like if you use these Pauli matrices like that, then you got to include a factor of 1/2. So, if you want to rotate pi over 2, when you exponentiate this little guy, you got to do like pi over 4. Sometimes you'll normalize your Paulis, like, so you multiply all the Paulis by 1/2 or something. Don't have to worry about that. But similarly, if we had to measure expectation value in the x direction, we could just do a little rotation of, say, negative pi over 2 around the y axis. And that's going to rotate x plus into z plus. So, just to like prove that like works, here's a little function, takes in a little qubit state. We get the expectation values of x, y, and z. Let's say this is like an x plus state, up plus down. Okay, if we look at its expectation values, we see, oh yeah, look at that, 1, 0, 0. Yeah, that's x, y, and z. So this is like pointed in the x plus direction. Then we can like take that state and rotate it around the y axis, negative pi over 2, and indeed it takes us to z plus. We could take this state, which is up plus I times down. That's y plus. Indeed, we look here and we see, oh yeah, 0, 1, 0. If we do a pi over 2 rotation around the x-axis, that rotates that guy into z plus. So that's great. So we can do the same thing before. We can, like, here, this function over here did the sort of dumb thing where we, just flip a random coin, classical or pseudo random coin, to get the expectation value in the z direction. We can use that same function to calculate these y and z expectation values by just doing the rotations first. And you see, we get basically the right answer up to some little error. Just going through it, just building it up step by step. So we have a matrix H, we decompose our matrix into a sum of Pauli's, and then for each term in that sum, we do a whole separate experiment: state preparation, pre-measurement rotation, and measurement in the z direction many, many times to accumulate the expectation value of that Pauli. Then we add them all up, all of those expectation values, each multiplied by the weight in the decomposition, and that gives us the expectation value of the original matrix on that state. So, you know, putting it together, we have this little function here. We takes an operator, expands it in the Pauli basis, and then for each term does the z expectation value on the rotated version multiplied by the weight, unless of course we're dealing with the identity, in which case we just add in this whatever the weight was as a constant term, and we get basically the right answer. So, you know, that solves our problem for the single qubit case, basically. If we can evaluate any 2x2 expectation value, and, you know, 2x2 operator, what's its expectation value on a quantum computer? We did it. We just have to decompose it in the Pauli basis, measure the expectation values of x, y, z separately, and multiply those expectation values by their weight in the Pauli decomposition, and that gives us the expectation value of the original operator.
Matt, can I ask a silly question?
Mm-hmm.
It seems to me that you could do this calculation more easily on a classical computer than on a quantum computer, or is it just that for higher order matrices?
Exactly. Yes, of course.
Advantage. Okay.
Of course, yeah. If you just have a 2x2 matrix, yeah, like don't waste your time. Just.
But even for higher order matrices, and again, I'm probably jumping the gun. It seems to me this can all be done on a classical computer. I don't see what the advantage of doing it on a quantum computer is.
It's like as you say, it's this is not doing anything that a classical computer can't do. I guess the theory is that if your matrix is big enough, it's going to be easier to take a whole bunch of these expectation values of Pauli's or whatever, and that's just going to be easier than actually finding the eigen decomposition of your matrix.
But
Yeah.
would it be easier on a quantum computer? I mean, even for a a large matrix?
Well, how do you mean? Yeah, I mean, because you don't have to actually calculate the eigen decomposition. All you have to do is just this, just do these rotations and then do the measurement again and again and again, and then you have it. You don't actually have to I mean, the one thing you do have to do, of course, is decompose your operator in the Pauli basis, which might not be trivial, but it's going to be easier than the eigen decomposition, right? Like we see here, really all you need to do that decomposition is just take a bunch of these traces. So, that's the cost of that is a matrix multiplication and a sum along the diagonal for each of the Pauli's. So that's not too bad. And oftentimes, if you're thinking about say the way the Ising model is presented, it's presented as the Hamiltonian is a bunch of Pauli's, right? It's a sum over, x on the one times x on the other, or z on the one times z on the other. The way that the Hamiltonian's presented to you anyway is as some expression in Pauli matrices, which is to say maybe you don't even have to decompose it in the sense that you just already know that.
Well, Pauli matrices are basis states for 2x2 matrices, but when you get up to higher order, it's a major task to decompose the matrix, isn't it?
Well, yeah,
Again, the question I'm asking is that will a quantum computer facilitate this more easily than a classical computer? Because I think where we're going with this is we want to show that a quantum computer can do this quicker.
yeah. So I mean, we're not gonna. I mean, we're not like it's not gonna be quicker. Like as you saw, like this does the thing. It took 20 minutes. Well, we had to wait in the queue or whatever. I'm not saying that in this instance it's faster because we're just working with very small matrices because we have tiny quantum computers. But yeah, in theory, it's like if your matrix is like 1 billion dimensions or something, like maybe it's probably it is going to be easier. Like you'll see, like in the end, when we do this, it's like the number of circuits that you have to evaluate. It's like you have to evaluate like a lot of circuits, hundreds of circuits again and again, which does seem kind of crazy. But if your matrix is really huge, finding the eigen decomposition is kind of a pain in the ass. But yeah, I mean, we're not using the quantum computer to find the decomposition. So there's two senses of decomposition, right? There's like decomposing the matrix as a sum of Pauli's, and then there's finding the eigen decomposition. And we assume that you already know this Pauli decomposition or like able to calculate that on a classical computer. And you're just using the quantum computer to like evaluate the actual expectation value. But yeah, as you say, so like what happens when we have multiple qubits? Can we pull the same trick? So it's kind of like an awesome fact that, the Pauli matrices form a basis for, 2x2 Hermitians. And it also turns out that strings of Pauli matrices of length n also form a basis for Hermitian matrices, which are 2 to the n by 2 to the n dimensions. And by a string of Pauli matrices, I mean a tensor product. So like this string of Pauli's is just shorthand for, X tensor Y, tensor Z, et cetera, et cetera, et cetera. So we can get a basis for, say, for example, if n was 2, 2 qubits, a basis for, 4 by 4 Hermitian matrices would be provided by these 16 matrices, which is just all the different combinations of them, or, not necessarily combinations, but. So that's great, and it works, for, as I say, for any n. We have 10 qubits. You take all the possible strings of Pauli's, X, Y, I, et cetera, like all the different, orders, and they can be repeated, et cetera, of length. What did I say? 10. All the Pauli strings of length 10. You get, a fuck ton of matrices, and they will form a basis for your operators. So, it's in that sense no more difficult to decompose an n-qubit operator. You just have to, take the trace with all those different Pauli's, strings of Pauli's in turn. So here's a little function that constructs that Pauli basis. We just start with the 2x2 Pauli's, and we just go through all the possible strings of them. We use product, little iter tools of length n, and we tensor them all up. We're going to use this as our example matrix, little 2x2. And we can decompose it and recompose it just as before. So for example, here's the matrix. We find its Pauli decomposition. There it is. And if we, multiply II plus XX plus YY plus ZZ, each weighted by these weights, of course, we get our original matrix back. So we can decompose this matrix as this, writing it as a weighted sum of strings of Pauli operators. And then as we know, the expectation value becomes this, So we can just take the expectation values of x, x, y, y, and z, z separately and weight them appropriately, and we get the full expectation value. Okay, so now like a little word about this. You know, it's a fact that if you take like 2 by 2, say, operators, A and B, and you just tensor them, like A tensor B, and then you act on a separable state. So like alpha and beta are just like 2 different qubits. They're in a separable state. Then if we just tensor A and B, acts on this little tensor state here that's separable, then what happens is it's just basically like A acting on alpha and B acting on beta. So these kind of like distribute over. So on a separable state, A tensor B just transforms the first state by A and the second state by B. And one of the things that implies is that the tensor products of A and B's eigenvectors are also eigenvectors of A tensor B. And moreover, the eigenvalues of A tensor B are given by products of the eigenvalues of A and B. So we can see that. So for example, we take xy, right? Tensor Pauli x and Pauli y. We find their, eigenstates. We go through them and we tensor them together. So we just, take the first eigenstate of x and tensor it with the first eigenstate of y, and then the second eigenstate of y, and then the second eigenstate of x, first eigenstate of y, etc. We get 4. And we also multiply the eigenvalues. Oh, typo. Oh, no, wait, I was right. Sorry. No typo, great. Okay, so we look at that. What am I showing you here? Okay, yeah, so these are the eigenvalues that we get. It's just the product of the eigenvalues of the individual eigenvectors of x and y. And what we want to see is like, okay, are they really eigenvectors? So what we see here is to the left is this tensor product of like x and y eigenvectors, and then we act on it with xy. And that's what appears in the second column here. And we just want to see, like, is it really an eigenvector? So for this guy, which had eigenvalue 1, when we act with xy on it, it leaves it exactly the same. Great, it really is an eigenvector with eigenvalue 1. Similarly for here, we look at this, we look at that, and they're just multiplied by -1, which is exactly what we want because the eigenvalue for that is -1. Similarly here, another -1 eigenvalue, and here, +1 eigenvalue. So indeed, it's true what I say, that the tensor products of the eigenvectors of these individual matrices are eigenvectors of the tensor product of those matrices. And the eigenvalues of the tensor product of those operators is given by the products of the eigenvalues of A and B. But there's a subtlety here, which, we should mention. So for example, like, let's just calculate, let's like have the computer calculate, be like, hey, computer, what are the eigenstates of X, Y? And it tells us this. Okay, we get the right answer for the eigenvalues. Two of them are 1 and 2 of them are -1. But hey, this looks completely different from this. What gives? And yet we do a little experiment. What we do here is we go over each of the eigenvectors which we obtained this way. And we expand it in the basis of the eigenvectors that we got this way. And when you do that, what you notice is that this guy looks like that. It's just got two components here, and these are 0. This guy, 2 components here, these are 0. This guy got 2 components here, 0 here, et cetera, et cetera, et cetera. So what is this telling us? So in this alternate basis here, the eigenvectors and eigenvalues are ordered -1, -1, 1, 1, okay? So this is saying that this guy can be written as a linear combination of the 2 eigenvectors with eigenvalue 1 in this alternative basis. This is saying that this guy can be written as a linear combination of the 2 eigenvectors with eigenvalue -1 in that other basis. And, you know, this guy, when we calculate it the other way, had eigenvalue 1. And indeed, these are the 2 eigenvectors with eigenvalue 1. This guy had eigenvalue -1, and it's a sum of the eigenvectors with eigenvalue -1 in the alternative basis. In other words, in the basis provided by the eigenvectors, which you know the computer calculated for us, the original eigenvectors that we got via this tensor product, they live in either the 1 or the -1 sector. In other words, they can be written as a sum of eigenstates in the other basis with the same eigenvalue. And, you know, the conclusion, like what this is telling us is that like the ambiguity there, the fact that we get different eigenvectors, you know, if we just do this, we take the tensor product of the eigenvectors of x and y separately, or if we just calculate the eigen decomposition like naively, we're not really getting 2 different answers. The ambiguity is due to the fact that there's a degeneracy. In other words, we have multiple eigenvalues that are the same. So that both answers are right. In other words, this answer, this can be written as a linear combination of these with the same eigenvalue. And this, you know, which in this case is -1. You know, this guy can be written as a linear combination of these guys with, you know, eigenvalue 1 or whatever. Yeah, 1. The other one was -1. So everything's okay. It's sort of, you know, that's sort of a subtle point, I guess. I just thought it was interesting to bring up. So in any case, we're good to go.
It looks like the alternative basis is just the original basis rotated by 45 degrees, because 707 is the square is 1 over the square root of 2. It's the sine of 45 degrees. So it looks like a 45-degree rotation. It's essentially what it is.
Yeah, maybe. I'd have to double check on that.
Well, 707 10678 is
Oh, that's definitely
1
true.
over the square root of 2.
Certainly. Yeah, no, that's definitely true. Yeah, I mean, it's not, it may or may not be obvious to you that if your matrix has, you know, multiple eigenvalues that are the same, that the eigen decomposition is like not unique. At a certain point, that was not obvious to me, and then I demonstrated it to myself, basically.
I'm just wondering. I mean, if it's a 45-degree rotation, then couldn't you have a basis at any rotation, at any arbitrary rotation?
Right. Well, so yeah, like so there could be many different like linear combinations, you know, as long as it's a linear combination that's like living in the eigenspace with eigenvalue 1 or the eigenspace with eigenvalue -1, you know, those will still like work basically. Now, like when you say, you know, it's just a rotation, like, do you mean a rotation of each of the two qubits individually, or, you know, I guess that was my, you know, the question I would ask.
I'm not sure. It's just that I recognize 707 as 1 over the square root of 2, which is the sine or cosine of 45 degrees. So it seems that that's just the rotation from the original basis.
Well, that's what, I mean, you know, you're going to get that, like if two components are the same and you normalize, you know, you're always going to get like 1 over the square root of 2. Similarly, if you have 4 components, because of the normalization, you're always going to get a half for each of them, like if they're the same value. So, okay. So if we have multiple qubits for each Pauli string in the decomposition of like our operator, you know, for example, x, y, y, we can follow the same rule as before, actually, just simply on each of the qubits. In other words, our rule before was like if we had, well, if we just had the identity, then we didn't do anything. We just like added the constant term. If we had, you know, z, we didn't have to do anything special either. We just had to actually measure the expectation value in the z direction, whatever. But for x and y, we had to do these like rotations first, specifically, you know, -π/2 around y or π/2 around x. And so we actually just do that separately on each of the qubits if we have multiple qubits. So like if we were working with like x, y, y, we'd do a z measurement on each of those qubits. But first, you know, we do a little rotation around the y-axis on the first qubit and a little rotation of around the x-axis on the second two. Upon measurement, you know, we'll get 3 bits, say 1, -1, 1, -1, 1, you know, which represent the results of the z measurement on each of the qubits. And then because of this fact that I emphasize up here, which is that the, you know, tensor products of eigenvectors of the operators, you know, separately are also eigenvectors of the full operator with eigenvalue given by the product of the eigenvalues of the original matrix, we just multiply those 3 results together to get the eigenvalue of the whole state, which is -1. So again, like if, you know, we have x, y, y, we do this pre-measurement rotation, little rotation around the x or the y-axis, depending on whether it's x or y. We do the z measurement, we get 1 or -1 each time, and then we multiply those together to get the eigenvalue that's, you know, associated to the whole state. And then to get the expectation value, we just do that a bunch of times. We add that to the pile and eventually divide by the number of experiments. And that gives us the expectation value of that particular string of Pauli operators, which is just one among many in this decomposition of our operator. And so we add those all up, multiplied by the weight in the decomposition, and that gives us the expectation value of our original operator. So putting it all together, here's like a little function that just takes an operator and, you know, that acts on like a qubit and like, you know, tensors it with identities. So it just acts on like one particular qubit. Here's a, you know, I just do this like, you know, like just, it's just, you know, this like little classical stochastic simulation here, basically. You know, this will do our expectation value in the z direction of like n qubits. So, you know, we want to do the number of shots, you know, it's like the number of times we like run the circuit or whatever. So, you know, 100, you know, 1,024 times, we go through each of the qubits. We get its density matrix. The, diagonal elements are the probabilities. We flip a coin, get 1 or -1 based on those probabilities. Then we project that qubit into that state that we measured. So we do the little projection into the 1 or the -1 eigenstate. And then we go to the next qubit, take its partial trace, flip the coin, get 1 or -1, and then project that qubit into that state, et cetera, et cetera, et cetera. Go through all the qubits. And then we get this list of choices, 1, -1, 1, whatever it is. Because because of this rule that, that I keep talking about, to get the eigenvalue of that whole thing, all we need to do is take the product of those obtained eigenvalues, and we get the eigenvalue of that whole thing, of that whole state. This qubit is up, down, up, down. And then we, just divide by the number of times that we did this experiment, 1024. And that's going to give us the, basically the z, expectation value, measure them all in the z direction. And again, that's all we need, because we can just, to take the expectation value of any operator, we just take it, we decompose it in the Pauli basis, and then go through each of the terms in the Pauli basis, and for each one, it's some string like x, y, y, or whatever, and we do the appropriate rotations, and then we do all the get the z expectation value, and we weight that by the weight in the Pauli decomposition and add it all up, and then boom, there you go. So, sorry. Doesn't like it if I, classic thing in Jupyter Notebook is that, you're running stuff depends on previous cells. You don't actually run the previous cells. Okay, there you go. It takes a surprisingly long time to do that. Just flip these pseudo random coins. Okay, anyway, so yeah, so boom, we can calculate the expectation value in the classic way, or we can do it in our fancy way that we just talked about, and we get basically the same answer. So great. So that that's the theory, right? Basically, what we now have the theoretical ability to measure arbitrary operators on our quantum computer. Given that our quantum computer is gives us n qubits, and all we can do is they all start in whatever the up state, so whatever initial state they give you, and you're allowed to do unitaries, and then at the end of the day, you get to measure them all in the z direction. That is not at all actually a limitation, because we can actually measure any arbitrary operator that way by first decomposing it, in the Pauli basis, and taking an expectation value separately for each of those terms, weighted by the coefficient and the decomposition. Each one, we first do these pre-measurement rotations, and then we're good. So we can take expectation values to our heart's content. But then, the other issue when, you want to do variational quantum eigensolver is you got to parameterize your state, right? Because the idea is what we want to do is okay, so we can evaluate this. We can evaluate this expectation value. What we want to do is find say the lowest eigenvalue and eigenvector. So, say we could parameterize our state by some theta, and then just run over all the thetas, or do something more complicated, some kind of gradient descent. until like we get, you know, the lowest possible value for this. So we have to choose some kind of ansatz, for our whatever, for our operator. Now we're like, I mean, this is sort of like cheating here. I'm just gonna, you know, I'm just gonna tell you like what's a good ansatz here. Which like I didn't even come up myself with, but so it goes. So, and you know, this is kind of the art. I mean, it's like when you look at a lot of this stuff that's going on, you know, it's like all about, like when you're thinking about like what people are doing these days and quantum, you know, like machine learning, and dealing with like parameterized circuits, like the whole art is like figuring out like, okay, I'm going to use as my ansatz, like, okay, a rotation on each of the qubits and then like a C naught and then like a whole layer of this and then a layer of this. Like, it's kind of like if you've done neural networks, it's like very similar. Like you're like making these choices like, okay, I'm going to have a layer of like these number of neurons and then this kind of layer and then that kind of layer and whatever. And then I'm going to like train all the weights. It's like very, very similar, like the way people do it, like in the quantum case now. It's just like you have these like layers of, okay, like rotations and then like entangling gates and then these kinds of gates, because you like have maybe some prior knowledge about like what kind of state you're looking for. And each of those individual gates has like some parameter. And then you like try to like, you know, do this like feedback loop where you like train those parameters. And that's the game. That's the game in town. That's the big game right now. Everyone's doing that. So for example, here's an ansatz. Like if you knew that, you know, basically the eigenstates of this guy are going to be like basically maximally entangled states. Like, I'm just going to tell you like that's true. And like just from that alone, you can come up with a good ansatz. In other words, here's what we're going to use. So basically, the ansatz is a Hadamard gate, tensor with the identity, and then a C naught gate, and then a little rotation of theta around the x-axis. And we write that as like some psi theta. So this whole ansatz is parameterized just by this angle. So like, what's this really doing, right? So the Hadamard gate is just this little 2x2 guy. It's actually like a Fourier transform operator, like a discrete Fourier transform operator, which we've talked about a little bit at some point before. You can check that like if you wedge, you know, say like X in between, you know, H dagger and H, you just get Z and vice versa. In other words, like Pauli X and Pauli Z are like Fourier transforms of each other. Okay, kind of cool. Here's C naught, classic gate. It flips the second qubit if the first qubit is down. So, you know, what this is doing is like if we start with this state up, we act on it with the Hadamard gate, which takes the first qubit into like an X eigenstate, specifically a superposition of up and down. So we start off, both qubits are up. Hadamard takes the first one into a superposition of up and down, okay? And then the C naught conditions whether we flip the second qubit on the first qubit. But the first qubit is in a superposition of being up and down. And so the combination of like Hadamard on the first and then C naught will take this state into the maximally entangled Bell state, you know, up plus down. So, you know, that's the first part of the ansatz. We're basically going to start with a maximally entangled state. And then we're going to rotate by some angle theta, which we haven't decided yet. We're going to rotate the first qubit by some angle theta. And so, you know, that's going to allow us to parameterize, you know, like lots of different maximally entangled states. So, you know, if theta was just like 0, then we just would have this maximally entangled state. But like, for example, if theta, you know, was whatever, like you rotate 180 degrees, you know, then you would get this, you know, the like down up plus up down state. So So you can get basically the different, correlated or anti-correlated states and so forth. So we have an ansatz, and then what we can do is, again, like in the simplest case, we can just iterate over the different values of theta to try to find the one that gives us our ground state. So putting it together, it's like, here's, the ansatz takes some theta, acts on, basically that's the vacuum state for us here, like this up state. That's just how our qubits start off in the quantum computer. Do our Hadamard, do the C naught, do a little rotation of theta, and we get a state, okay? So here's our matrix that we're gonna, work with. We're gonna calculate just like the eigenvalues and eigenvectors the usual way, just to make sure we're like on the right track here. Construct a little Pauli basis for 2 qubits. And we basically go through all of the different thetas, evaluate the expectation value using our function from before. This whole thing, like stochastic, like little parameter here, that's just like, are we gonna do like the coin flipping or not, basically. And for each, okay, so we get the expectation value of our operator on each of the different values of the ansatz for different theta, and we just find the one that minimizes the expectation value, and then we plot it. Okay, so here's our matrix. Turns out the lowest eigenvalue is -1, and the eigenvector is just that state. So that's just calculated the usual way. If here's like all the different values of theta, you gotta like divide up your 2 pi into like some number of, samples or whatever. And obviously the more samples you use, the better. For each theta, we get, expectation value, blah, 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 blah. And we look and, basically, we get this answer at the end. Now you're like looking at that, it's like, is that exactly this? And you're like, basically, yeah. So, this is really close to -1. The answer is basically, pi in the end. And that's pretty close to that. That being pi being like the right theta to use. And then this, it's like, it looks kind of wrong, but it's right. I mean, basically, the closer this gets to pi, this term's going to go to 0, this term's going to go to 0. This is real close to that, but you're like, wait. But it's all like multiplied by -1 and I, but that doesn't matter because, that's just a phase factor. You're multiplying the whole thing by -I, who cares? So here's a little graph. So for each of the different thetas, we get the expectation value. We find that like at pi, we get -1 is like the lowest eigenvalue. So, okay, so like that's all well and good, but like, we actually want to run that on the quantum computer. So, IBM has their quantum computers, as I say, and you work with their, software library, which I'm told is pronounced Qiskit. And so let's just talk a little bit about how this works. So import some stuff. Now, here's the thing. In order to do this, we have to like actually evaluate quite a lot of circuits. And so they sort of give you this little job manager, which is just useful in the sense that like you generate a bunch of circuits, and like basically like when you send the quantum computer stuff, you're basically, I think, only allowed to do like 75 circuits at a time. So your job manager will kind of bundle up all your circuits into packets of 75 at a time and then send them all over. If you recall, when we looked at this, see, like I literally just like this one, experiment, we submitted, like 4 whole jobs, which had to be evaluated to get the full answer. When you do this, you need there's like a little token system. Okay, so like when you get your IBM account, basically you're gonna get like a token. And then so to log in, basically, you would uncomment this line and paste your token in there. Samples here is the number of different theta values that we check. And shots is the number of times we run each circuit to accumulate the expectation value. And then, there's these parameters you can set. So for example, if classical, is true, then we use IBM's quantum, classical simulator that's in the cloud. If quantum is true, then we're going to use Vigo. It's one of the quantum computers. Or you can just sort of set which quantum computer you want. There's Yorktown, there's Melbourne, okay, whatever. Just some options. Okay, so this is just what we had before. This constructs the Pauli basis. This takes us operator into the Pauli basis, takes us back. This is quite the same. Okay, this is a little bit different. So, the IBM framework allows you, there's a built-in way actually to do parameterized circuits where you explicitly make a variable, and it's actually good to do that because you can then sort of combine well, you can, I think you can, you can sort of compile them without specifying, exactly which value of theta. It's more efficient. In fact, in this instance, I don't do that just for simplicity. So, basically quantum circuit creates a little quantum circuit with 2 qubits. This does Hadamard on, the first qubit, and then controlled knot, and then rotation of theta around the x-axis, and then it returns that little circuit. Basically, there's 3 ways you can run this code. One is to run it locally. One is to run it, non-locally in the cloud, either with, IBM's classical quantum simulator or the actual quantum computer. So if we run it locally, we use this QASM simulator. If we want to run it, in the cloud, as I say, because we have so many circuits, we're going to use this job manager. So we load up a provider, get the job manager, and then load up the backend. And backend name was defined, up here, whatever we wanted. That's the name of the quantum computer or whatever. So, we got to lay out our circuits. So we go over, all the different thetas. For each theta, we go through, we start off with the, so we go through the Paulis, and then we create our ansatz for that theta. We do the appropriate, rotations, pre-measurement rotations. We tell it okay, measure them all. And then we add that circuit to the pile. And, we get a whole bunch of circuits. To make it slightly more efficient, we quote unquote transpile the circuits, which just simplifies them. And then if we run it locally, we use this function execute, which runs all the circuits on that back end this number of times. Or if we are doing it, in the cloud, quantum or classical, we use this job manager guy. Run, get these circuits, back end, whatever. And then we get the results. And in the end, like what the results that are given to us are in the form of counts. This was the number that we got up. This is the number we got down, the z direction. So in order to convert that into, the form that we want, we get the counts, and divide it by the number of shots to get the probability, and multiply it by the eigenvalue, which is the product of, the eigenvalues of the individual Paulis for that one. And yeah, and then, it's basically the same as before. Now, one thing that's worth mentioning is that, like, if you want to play around with like actually simulating, the different, the actual like state vectors, you'll want to use the state vector simulator. So what we do at the end here is like, once we've figured out like what our, final theta is, we do a little state vector simulation, execute it on the ansatz evaluated at that theta, and then get the state vector, and that's going to give us, the actual, 4-dimensional little vector that we want, and then we plot it. So, so this again is just running it locally. Takes a second. I think the thing that takes the longest is just the transpiling it or whatever. And again, as I say, like normally, there's these built-in tools for like parameterized circuits, which you would want to use, but I don't in this case. So here you go. It's just the same as before. We just have, here's our matrix. This is the right answer. Go through all the different thetas, blip, 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 blip. And yeah, there we go. So we get basically pi, basically -1. This is real close. That's going to go to 0. That's going to go to 0. That's 0, doesn't look like it, but it is. And there you go. Bling. And, one thing that's cool is you can be like, yo, what actual circuits did you use? And so like, let's just draw 10 of them. And so, you can see these are all the transpiled circuits. It's like basically what you expect. I mean, there's like not that many simplifications I can do, but you see here, it's like, okay, Hadamard on the one, then the C naught, and then like the rotation, and then like the measurement in the Z direction on both of them. And they're all like basically of that form. Now, as I said, at the beginning, like, so we can actually run on the quantum computer. And so I did that here. Basically, like everything that this Jupyter notebook can do, this little command line tool can do as well. So I just ran it like this. You can choose the number of samples, number of shots, whether run it quantum, classical, or whatever backend you like. And by default, it's like the quantum computer known as Vigo. Okay, so, basically the same thing. Here's the matrix, there's the right answer, go through the thetas, sends it off to the quantum computer, and then this was actually calculated by a quantum computer. In other words, that's the final theta it got pretty close to -1, whatever. And here's the graph, and you look at it, you're like, yeah, that's great, that's beautiful. It's so real because it's kind of bumpy, It's like, that's real world data there, guys. Look at that. Like, it's not exact. Okay, cool. So there you go. In the end, the answer was that when theta equals pi, our ansatz is basically that, which up to phase, got that little -I, which doesn't matter, to the lowest eigenstate of h with eigenvalue -1. So, we can imagine more, fancier stuff, more elaborate, we could have like huge matrix, more elaborate ansatz. I believe ansatz is the plural of ansatz. Fancier algorithms to search through the parameters. And in the end, we, generate thousands and thousands and thousands of circuits that we run thousands and thousands of times. And in theory, that's going to let you, it seems extravagant at some level, but like in theory that, if your matrix is big enough, it'll be faster to do that than actually finding the ID composition on a classical computer. Like, how many circuits did we actually have here, by the way? Let's check. $240 circuits. 240 circuits, each evaluated how many times? What was it? What did I say? 4,000, about 4,000 times. Right, so we valued 240 circuits, each about 4,000 times, and we estimated. So, so this is an example of what's known as like a hybrid classical quantum algorithm. That was the joke here. I found this image somewhere, I didn't make this up. But, Mickey's orchestrating this sort of dialogue between classical and quantum. In other words, you have some like parameters that you're using that like, you have a bunch of numbers that are parameterizing like your quantum state, and you keep doing these like quantum experiments, you get some numbers back, and then you adjust those parameters, and then like do some more quantum experiments, and then like adjust your parameters, and then and in this way, you do a computation. So and this would be different than like either just doing entirely on a classical computer, or like entirely on a classical computer, or a quantum computer where like everything's quantum about it. This is sort of, like, and especially for these, small scale quantum, devices or whatever, like these kinds of algorithms are super important, where basically you're able to do something, a little more efficiently by having your classical and your quantum computer in a kind of dialogue. It's worth mentioning, if you look over here, so, these were the jobs. So if you like look at one of these, we can, get some more information about it. So, this one had 15 circuits. It took 43 seconds to run. It's kind of slow, but, hey, we're getting there. Give it, a decade. We'll get there. About 4,000 shots. And it even shows you the result, the measurement results here. Kind of cool. It even shows you here was, here's all the circuits. Look, like literally all 15 that were in this packet. For each of those circuits, we can look at like what exactly was that circuit. And, for each circuit, like here's, the quantum like assembly code that, generates it, or, the Qiskit code, Python code that would generate it. So it's kind of fun to poke around here, and you can like download it. So that's, this is nice because it's like, you run these things, and, it's kind of nice to, that kind of save all your data for you. So, if you didn't save it yourself, you could use it again later, basically. There's like maybe one or two other things I wanted to say, but that was the bulk of what I had. So if there's any questions or concerns. Anybody? Jamie likes it. Nice. Yeah, is there did you guys follow each of these steps? Is there anything I can go over again, maybe a little more slowly, or? Um, so probably next time. Well, coming up, like I have two things in mind. One is to go back and finally do this little lecture, which is about Majorana fermions and the SYK model, returning, to our investigations of wormholes way back when. But I may save that for, 2 weeks from now. Next time, I thought it would be interesting to talk about another quantum, computing system that's worth looking at besides IBM's, Xanadu's. I requested a cloud access to their new cloud, but I did not get it yet, for various reasons, basically. So, what these people are doing is quantum computing that's basically based around oscillators instead of qubits. Well, also qubits, but like oscillators. So basically, Strawberry Fields is like their, it's like the equivalent of Qiskit or whatever. It's like the basic framework. And Penny Lane is like the quantum machine learning framework. And why do I bring it up? Well, okay, I'll say two things about it, just for now. Okay, wait, I went Penny Lane. Yeah. So like, it's kind of cool. Like this is like a nice thing, right? So it's like you're dealing with variational quantum circuits. You can do this. They have a built-in tool, which we could have used here, for dealing with this algorithm, the quantum natural gradient. So like, for example, we just search through all of the thetas. And you might be like, well, that was sort of retarded. There's got to be a better way of doing that, right? So you're like, okay, well, you like use gradient descent or something. And yeah, like that would be a good idea. But there's an interesting problem with gradient descent in general, which is basically like, okay, so you have some loss function and you want to like take a step in a direction that minimizes your loss. And, you're like taking these steps in this like multi-dimensional space, which is like, whose like dimensions are given by the different like parameters, like in this case of our ansatz. But normally like gradient descent, it like, you're basically treating that as like a Euclidean space. But that's not the only way to do it. And in fact, it might be better to do it in like another kind of like reference frame, basically. And basically, could you do gradient descent like directly in so-called distribution space, or a space which is like invariant with respect to like the particular parameterization that you chose? And in order to do that, you basically use what's known as the Fisher information metric. The Fisher information matrix, like as a metric, in order to do the gradient descent. And then they have like this really cool way of like actually evaluating that metric tensor using a quantum computer itself. And so they talk about this here. So I thought I'd bring that up. This little tutorial is like worth, reading, if you're interested more about, how like to actually do, fancier kinds of like variational quantum algorithms, like in practice, you like probably would want to use something like this as you're searching through the parameters for your ansatz. The other reason, what we'll talk about actually though, next time, ideally, is, so one of the cool things about these guys, right, as I say, they have great, it's all based on photons and harmonic oscillators and stuff. And they have really great like tutorials, for example, worth looking at about, the different kinds of gates and stuff and like how photonic quantum computation works. And I bring it up because it's super relevant to, what we've been talking about. Like, for example, just last time, we were talking about, squeezing here, two-mode squeezing operator. We love it. That gives us, as we know, the two wedges of like Rindler space, or in a two-mode squeeze state, and the Unrow effect, et cetera, et cetera. I highly recommend looking at their, documentation here. And what's really cool, basically, is, it turns out that Gaussian states are very, efficiently simulatable using a classical computer. And Gaussian states of like an oscillating mode or whatever consists of stuff we're familiar with. In other words, they consist of basically the vacuum state, the coherent states, which are like displaced vacuum states, and like the squeeze states, as well as like the time evolved states in the, under the oscillator Hamiltonian. And they all just like basically look like, little Gaussian wave packets. While we're here, I may as well just show you, let me know if you guys are getting like you gotta go or whatever, but may as well just show you this as a little preview. Here we see we have a oscillator, and here is a graph of the probability of like where this guy is. So this is position, and this is probability of the different positions. Here's momentum, probability of the different momentums. We can get all the coherent states, which consists of basically displaced vacuum states. We love the coherent states. We can displace, X. We can displace P. We can also squeeze. And by the way, look what happens. Like squeezing. Like what's happened to that Q over there? It's turning into a spike. If we squeezed it an infinite amount, it would just be a position eigenstate. In other words, you can think about like the delta function, which gives you like, position here as being an infinitely squeezed state. And rotation is like, this is actually the harmonic oscillator Hamiltonian. And so it's just doing its little oscillating whatever. And so, these are the basic sort of Gaussian operations. And they're called Gaussian because like basically, these like functions are like Gaussians, just squeezed, pinched, like whatever. One of the things that's cool is that, and again, we'll talk about this in more detail next time. Wait, is this no? What this one? I'll explain how you get these pictures, basically. This is visualizing something called the Wigner quasi-probability distribution, which you can think of as like these two axes being like position and momentum. So you're sort of like simultaneously visualizing, position and momentum. we can get like two oscillator modes. Here's one and here's another one. And we can use our favorite Schwinger representation of a spin in terms of two oscillators. And we can actually do some cool visualizations. So for example, here, this is an X rotation. Here you see the like expectation values of the qubit, there it is. It's like rotating around the X direction. And here you can see the quasi probability distributions like evolving. This is a Z rotation. You can see that it's just a phase rotation, and a phase rotation is actually just rotation in this quasi probability plane, and so on and so forth. Now, one thing that's really cool is that like these operations of like rotations and stuff turn out to like also be Gaussian operations. And so actually, we can return to our spin statistics thing from before, where, we had the sort of like Atiyah's like system of, you got points in 3D, you get the constellations, and then you get these like exchange rotations. Before we simulated that sort of classically. And it turns out like all those exchange rotations are Gaussian operations. And so we can use strawberry fields basically to very efficiently simulate that little, Atiyah, Berry-Robbins spin statistics construction. So that's what we'll talk about next time, because I think that'll be kind of fun. We'll see how to efficiently simulate that. We'll go into a little bit about how to use Penny Lane and Xanadu systems. And I'll explain, what is a Wigner quasi probability distribution? How can you use these to get back, the position and momentum, distribution functions, and what the heck is going on here. And, we could see, I'll show you how to make these cool animations. So that's, that's what's coming up. Whoa. All right, so does anyone have any thoughts, concerns? Oh, Moshe says, thanks for the examples, great. Glad you liked it.
Thank you, Matthew.
Cool. Yeah, I guess I'll see you guys next week.
Take care, Matt, and thank you.
Sure thing. Adios.